is a really interesting one. Nobody knows about this. We don't have a picture about it. It's a Boeing Delta IV rocket fuel tank testing facility in Atlanta. And Krawinkler was working for the Austin company when we did this one. This is the world's biggest net, cargo net. That's the same type of cargo net that they put behind the pilots in a Boeing 747 cargo plane to keep the cargo from squashing the pilot if they have to crash land. This is a fuel tank for a Delta IV rocket, and this end on that fuel tank is a piece of aluminum casting mill that weighs, I think it's 16 tons. And there's a welded seam right around it. Now we worked with exponent failure analysis on this. They did the gas dynamics. If that seam ruptures, that end cap weighing 16 tons reaches supersonic speed in 10 milliseconds. And when that happens, the requirement was that we stop it before it hit the door, which is out here about 20 feet away. And the only way you do that is, of course, a dynamics problem. So you take the kinetic energy of that thing hitting this net and figure out how far the net has to stretch in order to stop it before it hits the door. And then you spec out the net, and some guy up in Seattle makes it. And the net actually isn't suspended that way. In the final analysis, it's suspended from the four corners, and the shackles each weigh a ton. Continuing on, we got into some regular structures. This pair of 5-story office buildings in Las Vegas, 8-story office building in Dallas, and then we got the crowning achievement of Krawinkler Luth Associates, the Grand California Hotel in Anaheim, California. At the time we did this, we had a couple of other Krawinkler PhDs with us, also from Senator. And this was the other project we did that was notable for its analytical techniques. This building has 7 wings. This is what it looks like right here. Okay? And then this piece sticking over here on the side is the convention center. And the monorail goes right through there, bisects this building. And the issue was where to put the expansion joints. There were a number of choices. One might think that the obvious was to put it right through where the monorail went through. Well, it turned out that wasn't really the right place to put it. We set it up, we didn't set it up, most of the Hassan set it up so that you could parametrically describe this building in a Excel spreadsheet, and then hit a button, and neither Hassan nor I can remember what the button said. Maybe most of you remember what the button said. But you hit a button, and it would, based on your parametric description and your location of the expansion joints, spit out a model that had all of the appropriate properties for SAP. And then do a dynamic analysis, bring all the results back in, put them back into the Excel spreadsheet, parse and pick out the appropriate variables and spit out the summary for you. So we could, in a matter of hours in an afternoon, go through and look at all the possible variations for the expansion joints. And I'm trying to remember where we ended up putting them. I think we have one over here, and one right there. I think this ended up being a T-section. Anyway. It was an interesting thing. It's quite a project. One thing about Helmut is he's very much the old craftsman. In addition to state-of-the-art engineering, he puts high value in craftsmanship. And so here's an example of this is a drawing we did of this truss, which is a real wood truss. Of course, it has a lot of steel in it as well. For the sheriff of Grand California, this lobby, if you ever go down there, all this stuff is non-structural. It's hanging from a structure that spans 70 feet, and the structure itself is only 10 inches deep, which is the farthest I've ever gone with that size bin. Other things that we did, we were doing downtown Disney at the same time. This is the monorail station. This is downtown Disney, some of the buildings down there. If you've been to Disneyland, you've seen all these buildings. The interesting thing about these, here is a plan. They're all sitting on another structure. This is our deck. There's an expansion joint that follows here, and here is one of the buildings. You see the gray is the gray beams, basically. The expansion joint above the deck is following the line here. This whole piece is sliding on the lower deck. This whole end of that building slides. This whole piece of the building slides on the deck below. So it's rather interesting structure. we had to build this bottom part before we knew what the top part was, and then basically adapted the top pieces to fit on top. We back up one.